Hello, today we're going to go over Honors Chemistry Chapter 3, Section 2 on the structure of the atom. So an atom is the smallest particle of an element that retains the chemical properties of that element. And we talked about splitting a bar of gold in half and continuing to split it until we got to the smallest particle that we possibly could, and that would be the atom. Protons are the positively charged particles that are found in the nucleus. Neutrons are the neutral particles also found in the nucleus, and they're roughly the same size as the protons. Electrons are much smaller and they're negatively charged, and they're found surrounding the nucleus. We have three models of the atom. So starting with the simplest, figure 1, this model shows the three subatomic particles that make up an atom, and it shows really approximately where they're located. So the nucleus is in the center and the electrons go around it. Model 2 has a more 3D view, but it still has the electrons traveling around the nucleus in rings, which is not very accurate. It is showing that the electrons are at different distances from the nucleus. So you can see the blue one is inside and the red are on the outside. Those are representing the energy levels. And then we have figure 3, which is probably the most recent model that you've seen, and it's the best one we have for the simplistic view. And it shows the electron cloud. So you guys have probably been taught that the electrons are in this cloudy area surrounding the nucleus. It also illustrates the fact that the nucleus is roughly 10 to the fourth, that's 10,000 times smaller than the atom. So they show the teeny tiny nucleus in the center, whereas the other two have a much larger nucleus. So in reality, the nucleus is teeny tiny. We would not even be able to see it if the atom was this large. Okay, so the truth is we're going to learn all about the electrons in Chapter 4. These are the actual shapes that the electrons are found in. And these are probability. So we use integrals, triple integrals, to find the wave function for the probability of where the electrons might be. But really, we don't know where the electrons are. They're constantly moving and disappearing and reappearing. So these are the various shapes that we will go over next chapter. When you put them all together, so you put all those strange shapes together, you can see that the basic formation of this is a sphere. So for this chapter, we are going to think of the energy levels as being spherical, like figure 3, like the figure we saw over here. So we're going to think of them as being spherical, even though they look like this. And the size of the atom is going to depend on the outermost energy level, which is also called the valence electron. So this very outer gray circle here is what we're going to call from there to the nucleus is what we're going to call the radius of the atom, which the radius tells us how big the atom is. All right, so we have the three particles that make up atoms that everybody should know: protons, neutrons, and electrons. And then we can go even smaller. I jokingly call them the subatomic particles because sub means less than. So subatomic means they're smaller than atoms. Subatomic, these are smaller than the particles that make up the atoms. And they are quarks and leptons. So here we have the atom. You can see it's about 10 to the negative 8 centimeters, which would be 10 to the negative 10th meters. And the nucleus, you can see the difference in their exponent, is roughly 10 to the 4th power. This is 10 to the 4th times smaller the nucleus is. In the nucleus, we have the proton, which is 10 to the negative 13th centimeters. And then surrounding that nucleus, we have our electrons going around. And it has a radius of 10 to the negative 6 centimeters. Okay, and over here we have quarks. So the proton is made up of 3 quarks, and we're going to go over that in a second. So what makes up the protons is these tiny quarks, and you can see that they're roughly the same size as an electron. All right, so here's another breakdown of the particles that make up matter. We have hadrons, which are things made of quarks, and leptons. Hadrons are made of quarks. Baryons are made up of 3 quarks, and we just said a proton is made of 3 quarks. So a proton is a type of baryon, which is a type of hadron, which is a type of particle. Okay, and then we have these mesons, which are made up of 1 quark and 1 antiquark. We're not going to learn much about them. You can research that on your own. And then lastly, the neutrons are basically the opposite of protons. So protons are made of 2 up and 1 down quark. And I like to remember that because protons are positive. So it's 2 thumbs up and 1 thumb down. And the neutrons are made up of 2 down quarks and 1 up quark, the opposite of protons. Okay, leptons we're going to see in a second. The electron falls under this category. So an electron is a type of lepton. And here are all of the types of particles that we have. So quarks, you don't have to memorize this chart at all, but I do want you to know that there are 6 types of quarks. Protons and neutrons are made of up and down quarks. And here are the others. Leptons, you don't have to memorize either, but I do want you to know that the electron is a type of lepton. Okay, and then we have these strange things over here. These force carriers like the gluon, which they call gluon because it glues the stuff together, and the Higgs boson that was recently in the last 10-15 years discovered. Okay, if you click on this, the link is to an interactive website where you can learn more about it, but you're going to have to do that on your own time because that's all we're going to go over. The discovery of the electron. J.J. Thomson discovered the electron in 1897 with his cathode ray tube. And so the evidence that he found from his experimenting with the cathode ray tube was that cathode rays were deflected by a magnetic field, the same way a wire carrying an electric current, which was known to be negative, reacted to that magnetic field. And he also noticed that the rays were deflected by negative objects. And there's a really good picture in your textbook of the cathode ray tube being deflected by a magnet. So I highly suggest you look at that in chapter 3 of your textbook. And he noticed that any electrode, so the anode and the cathode, were made of metals and different elements. And anything that he put there produced the same ray. Okay, so he claimed from his evidence that the ray was negatively charged. Why is that? The reasoning you guys need to write out. Why did he conclude that they were negatively charged? Well, the ray that went across was behaving in the same manner as these negative things up here. So he knew these to be negative, and the ray was acting the same way. So his reasoning was, because they behaved as the other negative objects, that this ray that goes across was also negative. And all the elements had the same particle inside of them. And the reasoning is because every electrode produced the same ray, therefore every element must have the same negative particle inside. Okay, and you guys have a box to draw the picture of the cathode ray. You can draw this one, or you can draw the one in your textbook. It's a little simpler. The discovery of the nucleus. In 1911, Ernest Rutherford used his gold foil experiment to discover the nucleus. So his evidence was he shot at a piece of gold foil with alpha particles, which are positively charged, and most of them went straight through, which he expected. He expected it to be like shooting a bullet at a tissue paper. So he expected everything to go straight through. However, a few of them were deflected, and that was very unexpected. So he came up with the claim that because those positive alpha particles were deflected or bounced back, that the nucleus must be positively charged. It's very dense because it could deflect the alpha particles. And it was tiny because most of them did go straight through. You're going to see a picture of that in a second. Okay, so here is Rutherford's model right here. So he said that the nucleus is tiny because most of these alpha particles, that's the black line, went straight through the gold atoms. Okay, they went straight through. The ones that were deflected or bent those came near the positive nucleus, and the ones that bounced back actually hit the nucleus or got close enough that they were pushed straight backwards. Okay, so here is what he expected on the left. This is based on J.J. Thomson's plum pudding model. So he thought we had this big blob of positive charges with the little negative electrons stuck in there. And Rutherford proved that wrong when he found that actually some of these were deflected or bounced back when the little alpha particles were shot at this piece of gold foil. Okay, and lastly, nuclear forces. So the center of the atom has all of the protons, which are positively charged, and the neutrons, which are neutral, crammed into this teeny tiny little space right here. So all of the positive charges are shoved in the center of the atom, and all of the negatives are way far away from them. So how do all of those protons and the neutral neutrons stay held together so tightly in the center of the atom? Well, that is called the strong nuclear force. And it is a really strong force that has enough energy to create the atomic bomb. And it is what glues those protons and neutrons together in the nucleus. So the strong nuclear force holds the protons together and keeps the atom from exploding spontaneously. All right, have a wonderful day.